Welcome.
Hey, I'm Mayank Sanganaria. This is Werner, and we're going to present BitBending, circuit bending brought to software. Just a quick overview of what we're going to talk about. We're going to take a brief look at circuit bending and what it really is. We're also going to talk about some aesthetic ideas. We're going to situate circuit bending musically and culturally, and then we're going to talk about the important ideas that circuit bending lives by that we want to preserve, even though we're going to make it in software, and why we want to model it. Then we'll talk about a particular kind of circuit bending, which we term BitBending, thanks to Jorge. And then we present our implementation in software of BitBending. So what is circuit bending? It's a process of creatively modifying or augmenting sound-producing electronic devices. What kind of devices are we talking about? Typically, these are toy instruments, guitar effect pedals, just any kind of old analog come digital sound-producing electronic circuits. And it's based more on experimentation than on engineering, and there's a very strong anti-theory movement associated with it. And now Kurt's going to talk about some specific circuit bending.
So, as I talk about what circuit bending is, I'll give some examples. I'll talk a little bit about the history, the past, and the present. And I'll briefly introduce a lot of the aesthetic ideas and movements it's been associated with, how it's useful compositionally and musically. Let's start off with some examples, since I think a lot of people aren't actually familiar with it or don't have the sound of the real-world devices in their ear. Video. I'll leave that without comment for now and show one more.
I think that E.T. was using to...
Correct.
Good.
It's also notable for being, I think, the first speech synthesis chip used in a commercial product. It does 10-voter linear predictive coding. There's some, Texas Instruments made it. So let me show you just a couple of pictures and some more sounds of some of the pieces I've made over the years before we dig into what circuit bending is. This is what we just heard. It's a circuit bent music box, kind of children's toy. If I remember, it was shaped like a turtle and plays various lullabies and such. It made it at the end of high school. Here's the speak and spell we just heard. I'll play a better recording of a wider variety of the types of sounds it can make to further get this sound in your ear. I made this around 2007, and it's shown here with the MIDI control, but you can sequence it with the computer. You guys might have seen my modulations show last year. A lot of the gnarly sounds from that were actually this sequence lockstep with the computer. The speak and swell is actually one of these kind of holy grails of circuit bending. People do a lot of work with them because the old chip has a lot of potential for making a really huge variety of sounds. People, tons and tons of people have done many, many different versions of them. They're real famous. Another really famous object of circuit bending are the Casio SK line of keyboards. So here are two I did that have patch bays on them, and you can sequence these as well. And so here's the sound of this kind of thing. So this, take note of the box on the far left-hand side. We're eventually going to introduce this technique, BitBending, and our software model of it. And that box is actually the physical implementation of BitBending. As well, here's one more example that we'll be hearing throughout the presentation. These are two circuit bent drum machines, 80s ones, Roland 505 and 626. This was rate one Roland switched to digital symbols in their drum machines. So these don't have the kind of cherished analog sounds of the 808 and everything, but they're very nice, fertile devices for circuit bending. Notice again the breakout box. This is another real-world physical implementation of BitBending that you'll know more about the computer model of later. So let me talk real briefly about the history of circuit bending, if you guys aren't familiar with it. It traces its history arguably back to the very first electronic musical instrument, the theremin. It was invented by Leon Theremin in Russia in 1919. And it was patented in 1928. It was arguably the first electronic musical instrument ever created, and certainly the first one mass manufactured and produced. Leon Theremin had a wildly successful tour throughout the United States to publicize it. There are quite a few very talented, brilliant Theremin players also toured with him, Clara Rockmore and such. And it was actually invented, like many great things, by accident. He was working as a technician or doing some research with radio tubes, and kind of one of the heterodyne oscillators in the radio tube accidentally got messed up to play audible frequencies, and that was the principle that he exploited to let the theremin play. Another important figure in the history of circuit bending is Reed Ghazala. So in the 1960s, he invented the term circuit bending. He did a lot of the early work on it. I think he might be the one that says this, but he's been called the father of circuit bending, possibly self-appointed. He read this really great article called The Folk Music of Chance Electronics. He published a whole series of articles in the 80s in maybe Sound on Sound, I think, and wrote a book called Circuit Bending, Build Your Own Alien Instruments, that's real popular nowadays. We have a copy in the library, or we would if it weren't sitting on our kitchen table right now. It's coming back tomorrow. So, yeah, this is an example of one of his pieces. He paints them all, and he did a lot for popularizing this and kind of laying some of the groundwork for it to be solidified into like a scene rather than a bunch of people doing disparate work on their own. Notably, he came across circuit bending, the idea of exploiting this chance electronics to produce new things, when he was also messing around with it in radio, only this time transistor radio. Nowadays, circuit bending is a pretty big thing. A lot of people in the do-it-yourself community and these hardware hacking groups are very into it. There are workshops and festivals based around it. There's a few people and a few groups that are doing a lot of work to popularize it and help create these communities where people share information. These three people and groups are worth mentioning. Burnkit 2600, a group of 3 people from New York, and they put on a really great show, kind of mixing chip music and circuit bending. They also host a pretty extensive website where people share information about how they bend different devices. They share some of their own schematics. Nicholas Kahns is a professor at the School of the Art Institute of Chicago. He wrote this really great book, Handmade Electronic Music, that I kind of found out about a few years ago. And it's really it's a really helpful book about how to circuit bend and how to get at hacking your own electronic devices and building simple things from scratch. It doesn't necessarily assume a whole lot of background. It gives you a lot of tools you need to solder and do different things. Pete Edwards, or Casper Electronics, is another guy from New York, Troy, New York. Actually, he's in residence at STEAM right now in the Netherlands, at the Institute of Technology, doing modular synth design, kind of experimental modular synth design. And again, he hosts a whole lot of his own schematics up online and answers questions, and people share all their information through that venue. So this is part of the main cultural association of circuit bending right now, this free exchange of information between people. Aesthetically, circuit bending is complicated. It gets at a lot of different ideas. It kind of exists at this nexus of all sorts of things. So let me try to present a justification for why we should be interested in it, why some people like it, what sort of things it gloms onto, what sort of ideas it taps into. Some people like it just for the sound. People find the sounds themselves charming or the process creatively fertile. A lot of types of composition or music thrive on compositional constraints, and getting into a piece of old hardware and hacking it apart and trying to get the sounds out of it is a very constrained process, yet one that can be really creatively fertile. Now that you've got a little bit of the sound in your ear, this reference might make sense to you. Luigi Russolo was an Italian futurist who wrote this manifesto called The Art of Noises in the early 20th century. And this manifesto is really worth looking into and really applicable to circuit bending. It sought to justify like the emancipation of noise and everyday sounds of all sorts from orchestral music, and say that serious music could have any sort of sound, and value judgments shouldn't be made about the prettiness or usability of the sound beforehand. Circuit bending has found a lot of resonance with kind of this noise music aesthetic that found its roots here with Luigi Russolo's work. Nowadays, there's a lot of associations that brings to the table with respect to nostalgia for these old consumer electronic devices. A lot of people in our generation grew up playing with these toys, Casio keyboards and sound-reducing things, at the advent of really cheap integrated circuits. And so, in addition to the sounds being charming on their own, just for their sonic properties, it brings a lot of these associations to the table. The thing that actually excites me the most about it from a sonic standpoint is this idea of multi-scale sound design. Stockhausen introduces, well, I think he did some of the early work on talking about sound existing on multiple levels in his article, How Time Passes. It was somewhat concerned with serialism and serializing multi-scale sound design of compositions in the classical 12-tone serial aesthetic. But later work is done by Curtis Rhodes. He's a professor down at UCSB. And his is a book, Microsounds. It's all about every single type of granular synthesis you could ever care about and more. But actually, my favorite part of the book is actually the first 2 chapters. He talks about time, every time scale from the Planck instant to the heat, or the Planck unit of time to the heat death of the universe, and the implications of each one for musical sound. It's really worth checking out. Thought I had one more line on here. What he focuses on that I think is really important for circuit bending are the border between these time scales. Let me introduce this idea of borders. We'll get back to it a lot and speak a lot more about this later. But part of the idea that he introduces that's really great, and I find a lot of resonance with, and I think is very important for composition and very resonant with circuit bending as an aesthetic, is borders. So he talks about sonic objects that are on the border between a note and a gesture, things that are on the border between a gesture and a phrase, things on the border between a phrase and a composition, and we'll find a lot of that. And even further down the time scale, things on the border between timbre and musical material. So if we want, now that we've kind of introduced the idea of circuit bending, are there any questions on that before we move on? Okay. So software modeling is something we try to do a lot for music. You want to ask the question, what is a successful model for circuit bending? And kind of a related question, why can't we just sample it? Julius gets at a really good explanation of this in his book, Physical Audio and Signal Processing. And you gave an example in class the other day that I think is pretty applicable about the piano, how it's a very monumental task to try to sample even a well-constrained instrument like the piano that can't do glossanos, that can't do many different types of articulation. It's a hugely memory-intensive, monumental, difficult task to model a few different velocities of all the keys. And even that doesn't get a lot of the interesting interactions between the notes as the sustain pedal is held down, and so on. It's even more difficult for stringed instruments. It's maybe impossible for these electronic devices that leverage feedback and like atypical, non-intended behavior of circuits to create sounds. So a successful model would allow you to get at all the interesting sounds and have the same experience of like a creatively fertile, exploratory experience when you're using the instrument. And it would still sound the same. It would still have all the same sonic properties and interesting characteristics in the timbre domain. So moving along, Mike can talk a little bit more about software modeling.
So now that we know what is important to preserve while making a software model of circuit bending, we should also look at some of the advantages that we get for using software modeling. So the first one is scalability. These devices have been out of production for the most part for decades now, and getting electronic circuits that actually are malleable is really hard to find these days because people have just moved to using ICs that do everything on the chip. And finding these old devices is becoming hard, and as a result, it's really expensive to find. In addition, it provides an archival utility. These devices are getting hard to find, and maybe in the future people wouldn't even know that these devices existed and what happened with them. So it serves an archival use as well. In addition, it also is extendable to things that we cannot do in the physical world. Once we have a model, we can try out even more things than is possible. And one of the biggest advantages is that once we have a software model, it can conveniently fit into existing workflows. One of the challenges that I feel with using circuit bending and performance is just the fact that you have to carry around this toy and you have to use that in your performance, whereas a lot of other electronic music workflows are restricted to the laptop. So now you're carrying around a laptop, and then with the laptop you're just carrying around 5 or 6 different toys. So once we have a software model, this is a huge advantage that we get. So now, bit bending. What is bit bending? To explain this, first we'll play some types of bends that are specifically bit bending rather than just any kind of circuit bending. We'll explain why we chose bit bending to be the one that we modeled first up. And we're going to go into detail about counters, because that's the example that we have in detail to present. So there are 2 types of bit bends that we look at. One is clock bends, and the other is drum bends. So this is what a clock bend sounds like. So yeah, once you change the sampling rate of the clock, the pitch kind of changes. And that's a drum bend. So what exactly is bit bending? Given a circuit where we have serial information being transferred between chip X and chip Y, we put in our own digital logic between these chips, and that is essentially what bit bending is. So that was another example where the first 3 beats were not bit bent, and the second 3 beats were bit bent.
That was the roll-in drum machine you guys saw a picture of earlier.
We can do it again. Now, Kurt's going to talk a bit more about why we chose bit bending to model.
So I came across this technique when I was rebuilding clock circuits from scratch for a couple devices I was doing pieces out of. One thing I found to be really expedient when building clock circuits was the ability to do exact octave transpositions. So I built a sort of astable multi-vibrator NAND gate clock, and I would feed that into a counter and select different pins off of the counter. For those of you who aren't familiar with digital counters, we'll do an introduction on how exactly they work, since we're going to trace that example through our model in the real world. We'll do that next. So I was doing this to get octave transpositions, and I had the idea to extend this to non-clock signals. So I tried that out and found it to be really exciting and get some good sounds. That's actually what we just heard from the drum machine. Then I decided to extend it to non-counter logical operations to send signals through other integrated circuits, NAND gates, OR gates, and so on. What's really nice about this, aesthetically, versus just poking around with wires and trying any old thing out, is it's kind of predictable. With certain classes of signals, we kind of know what we'll look at. If it's a square wave, you know exactly what we'll get out of a counter. And as we'll get at in a little bit, there are certain properties of this modification that are really predictable and happen time and time again, regardless of the nature of the signal. As well, we found that we can model ideal behavior of the circuit without getting in the fact that counters and these digital logic chips aren't black boxes, but they're really constructed of real-world transistors. We found that we can get very good behavior even treating them as ideal. And the distortion and interesting behavior comes from the mangling up of the bits, not from the nonlinear, non-idealized circuit behavior. Another thing that's cool about using digital logic in a compositional sense is that it gets at this idea of using mathematical operations as a compositional device. This has been around for a long time. People would even argue that Bach uses the idea of permutation in his contrapuntal work. Many of his works, like the Art of Fugue, deal with working out every single possible mathematical permutation of subjects and counter subjects and subjects against one another. The Greek composer Ioannis Xenakis in the 20th century wrote a book called Formalized Music that was all about performing logical operations with sieves and other number theory type of things, and using that to generate normally traditional notated music, although he did a few electronic pieces as well. And I actually just heard about this guy just the other day from Ivan. Victor Ordan, he wrote a whole thesis out at MIT a few years ago about one-bit music. And again, it's getting at this idea of using logical operations on binary signals to produce music as a compositional device. So circuit bending taps, or bit bending in particular, as a subclass of circuit bending, taps into this tradition by using logical operations and counter operations as operations on timbre and on the information flowing between things. And this will both modify the sound and generate musical material, as we will see soon. Also, it sounds good. It can be an exciting sound. So let's quick explain what a counter is, in case people aren't familiar with it. Counters are integrated circuits that take in a signal, usually called a clock pulse. On a rising edge, they'll increment their count. So they're counting in binary. And when they get a rising signal coming in, they'll increment their value, and all their pinouts represent their current state as a binary number, where high voltages are ones and low voltages are zeros. So here's an example of bit bending with a counter. So we see our diagram we saw before, only instead of the abstract idea of any old digital logic inserted between two chips, we have a counter. So let me introduce a process for analyzing bit bending that we're going to use throughout this talk, which is taking successive pins off a counter IC. So we have one signal on the actual Roland 626 drum machine, and we send it into the counter, and then we take successively more and more significant bits off of the counter. So let's do that. So let's see a spectrogram of that, I think. So, no, just keep that in mind. We'll come back to it. Here's an example of what a counter does to white noise. So in this example, we've taken white noise as a uniform distribution of zeros and ones, fed it through our counter model, and then converted each group of 16 bits back to a float. So you can see a graphical representation here, I'll play it as well, of the sort of behavior you put in the drum machine. Every successive, more significant bit off the counter produces a kind of either transposition or octave narrowing of the bandwidth. It also makes the signal tend towards a square wave in all cases. A square wave will remain a square wave exactly, but even white noise will tend towards a square wave eventually. As the sound gets lower and lower, it eventually will cross the threshold of sound that's audible as pitch and enter the rhythm territory. You can see that at the end as tone, and you'll hear it as tones become rhythmic pulses below 20 hertz or so. So this one, let's play this. Okay, so this is a really interesting idea because at every successive more significant bit, we get kind of a predictable behavior. It's kind of like a transposition locally. But over time, it also shapes the sound from being completely spectrally flat towards being a harmonic sound. So it's actually quite distinct from just a straight transposition or a sample rate conversion, for instance. Other things that share this property of sounding like a narrowing of bandwidth or a transposition. Here's the same drum example from before, only with a spectrogram, and we'll see if we can see some of the same features in this. Keep in mind, it's not the exact same process that's happening. Actually, I don't know what pinouts are happening on the drum machine. They're just some pins. But we'll see some of the same features in the spectrogram of the sound. Especially near the end, the octave lowering, bandwidth narrowing sound should be very apparent. But again, what's really interesting is any signal will tend towards being a square wave. So this picks up all the properties of a square wave. There's integer, all the harmonics in the correct places and amplitude that you would expect for a square wave, even though it started off its life as a drum loop. So we've given a really brief explanation of circuit bending and how it situates in like this sonic world and the culture of it, and some of the extra sonic things we might consider. And we've introduced BitBending, this technique that we came up with for real-world circuit bent devices using logic chips interpolated between serial exchanges. Now it's time to look at our software model of BitBending, which is our first look at modeling circuit bending instruments on the computer. The first thing we should do is listen to it. Here, this is like a minute and a half of just the different types of sound our model produces. And like before, I'll leave this without comment, and we'll talk about it, and you'll understand parts of it as we go. Oh, so, get code and sound. This is the all from software model. So Mayank will tell us more about how the model works.
So BitBending in software. We'll take a top-down look at the library, going from what the ideas were to the actual implementation and use. We'll also talk in detail about an example, which is an FM synthesis made with numerically controlled oscillators. We'll compare how our model sounds with, or how our model compares with a real-world devices. So, in keeping true with the 80s philosophy, that's the background. And so that's a circuit board on which we'll have chips which have inputs and outputs, and each of these inputs and outputs will have registers. The chip inputs and outputs are abstracted into a chip I/O class, and once that happens, these are the kind of inputs and outputs that we model at the moment. So edge-triggered input, serial input, phase accumulator, single-bit input, and serial output and single-bit output. These are the chips that we've modeled at the moment. So there are two groups right now. The one on the left is our chips that have timing information, and the ones on the right don't have timing information. So, for example, a delay chip is going to take a clock input and do some particular calculation once the clock reset is received, whereas all the chips on the right continuously update their output based on their inputs. So this is how we'll use it. It's kind of similar to register transfer level that's used in VHDL, because that's the level at which we want to access and mangle the data. So you start off instantiating a circuit board and all the chips that you want. You initialize them by actually making the connections on the board that you want, and initializing all the chips to the values that you want them to be at, and then you use them. You just simply take you just simply make a tap on the output of any chip that you're interested in, and then you can take the float value and convert it to the audio. So we chose a numerically controlled oscillator to be what we modeled with our library first. Why did we do that? One, it was really simple to make, and the second, it fits nicely into any synthesis framework. This is what a numerically controlled oscillator is. It takes in a frequency controlled word, and that gives out binary serial information to a phase accumulator, which continuously accumulates the phase based on the timer, based on the clock inputs, and that in turn gives out its phase to a sign. It could be a wave table, for instance, and that would actually give out the sine wave. A numerically controlled oscillator is used in function generators and communication systems, and sometimes in sound synthesis. So we implemented a 2-operator FM synthesis. This is what it looks like. We have a frequency control word that goes to a phase accumulator that actually looks up into a sine wave. And we multiplied this with an ADSR so that we can control what that sounds like. And then we have the carrier. So the output of the modulator goes straight into the carrier, and then we get the output of the FM. Now Kurt will talk about some of the bends that we put into this system and compare how it sounds.
We covered this already. So another reason we chose FM as a first experimental model of this is because circuit bending gets at some of the great things about FM synthesis. Our model, as you heard, can create a huge, very wide taxonomy of different sounds from only a few simple changes. All the sounds you heard don't actually reach beyond this simple 2-operator FM synthesis model, but it can produce all those different sounds. As well, it's implementable with numerically controlled oscillators, as Mayank explained. This is our model in its normal operating behavior, just doing simple 2-operator FM sounds. You might hear some modulation index sweeps and some changes in the ADSR. Let's go back to that. So this should at least sound familiar to DX7 classic FM synthesis sounds, if a bit inelegantly composed. So here's an example of one bend we did, and we'll show it in isolation, not within this whole range of taxonomy of sounds we can get. So we start with our model, and in the spirit of bit bending, we've taken one of the serial information paths, that is the one between the phase to amplitude converter and the multiplier in the carrier operator, and we've interpolated a counter. And so we'll take successive, more significant bits off the counter and show how that will affect the sound, just like we did with the white noise example and the real world drum machine. So again, the model shares a lot of the same behavior with the mathematical model of a counter and with our real-world counter bend on the drum machine. Here's another example. We'll apply the same technique to a different point in the signal path. So in this case, the counter has been interpolated along the serial path between the phase accumulator and the multiplier in the modulator operator. And we'll again take successive more significant bits off of the counter and show the sound of that. In this case, yeah. So here we start to see a little bit more complicated behavior rather than just this straight monotonic drive from white noise to a square wave. So here's a side-by-side comparison of just the plots of the short-time Fourier transform of the white noise example, the white noise example, the drum machine, the first counter operation on our model, and the second counter operation. And so you can see the features that are in common between them, just graphically, the ones we've already spoken a little bit about. So we trace this idea of the counter through them, but there's one other thing. I think one other thing that's probably worth going into in this talk is the idea of the bit depth. So when you allow the system to have a different bit depth, you change a lot of the features of it. So I'll show a couple of examples, one where this affects just the pitches that are available and explain why that could be important from a compositional standpoint and how that ties into a couple existing traditions of how we treat temperament and pitch. And one on the timbre and one showing how that operates on this border between timbre modifications and aleatoric pitch and sequence generation. So here's a little melody, and we'll successfully reduce the amount, we'll bit starve the thing basically. It starts off at 16 bits, and every half phrase or so it's going to drop a few bits. And as it goes, the amount of bits available to represent the pitch information are fewer, and so there are wider and wider grains of pitch accuracy. And this has the basic effect of detuning what's going on. Into trouble at the end. So you can think about this sort of operation as analogous to a bit crusher, which is a digital audio effect we're probably most of us familiar with. Although bit crushers only operate on the actual amplitude of a signal, this is operating on the way the information is encoded on various different levels. The amplitude, you'll see that it gets noisier as well as you go. And so it operates on the amplitude, it operates on the way pitch is encoded, it operates on the way phase increments are encoded, it operates on the accuracy of the wavetable, it operates on the accuracy of the ADSR envelope and the multiplier's accuracy. So it's manifested both as being detuned and as timbre modifications and as a signal to noise modification like a normal bit crusher. Let's show the same thing for just static tone timbres that exploit FM synthesis. So again, this quantization happens at all points of the signal flow. We get amplitude quantization. We also have quantization in pitch accuracy of the modulator, which is tantamount to quantizing the pitch of the modulator as well as changing its waveform. That's where the traditional bit crusher effect comes in. One more example, this shows how a really noisy signal can be decomposed through this counter down to an aleatoric signal sequence generator. And this gets at some of the exciting borders between timbre and actual musical material on the level of notes and sonic objects, and how these sorts of techniques can expose some of the underlying structure of the noise and the signals that are mostly passing by unnoticed and transparent to us. We have a few more examples of different bends, but since we don't want this to run too long and we want to leave time for questions, let's skip over a couple of these. These are examples. So, in conclusion, we want to make the point that circuit bending is really understudied in the academic community, even though it's a kind of thriving subculture and musical movement. It has been for a long time. Bit bending gets at this balance between being able to predict what happens in a certain circumstance and still giving exciting, unexpected, creative referral results when deployed in the use of modifying digital instruments for circuit bending. As well, we like to make the case that modeling, though it may seem antithetical to the kind of hacker, do-it-yourself, get your hands dirty with a soldering iron and two alligator clips ethos of circuit bending, is actually something that really extends that and is commensurate with it. There's a lot of digital art that's being done in images that has completely made the jump from real-world devices and to just looking at the way images are encoded and exploiting artifacts and JPEG compression and stuff. There's this guy, Philip David Stearns in New York. He just finished this year-long project called Year of the Glitch, where every day he would post some sort of image and tutorial about how to exploit these JPEG compression artifacts, and he made a lot of art with that and prints it onto textiles, and it's really nice stuff. So the visual community has already made this jump, and an analogous thing is kind of present in audio as well. And we want to make the case too that these early experiments we've done exhibit some of the desirable features of real-world circuit bent devices, and then we can take that further and get closer and end up with models that are even more exciting and even closer to the real thing. And Mayank will talk a little bit about the future, the work that's still yet to be done.
So, one of the things that we haven't gotten at yet is to allow feedback, which is important because it's one of the most important things that circuit bending has. Another problem that we have right now is that our model only does digital circuits, whereas all the real-world devices are a hybrid of analog and digital. So we would like to extend our model to include analog components. Another thing that we would like to get at is combining with the existing numerical models that are there for circuit modeling. We've modeled ideal chip behavior and we're happy with the sonic results that we've got till now, but modeling the non-idealized behavior could also lead to some really interesting results. We've got this library and we've made one example of it, but we want to be extending it to some more circuits that are there, and eventually we would like to model the speak and spell, which is the holy grail. One of the biggest challenges that we face are the interface challenges. Circuit bending depends a lot on the chance discovery of things, and we want to preserve that with our modeling. But at the same time, it's kind of hard to have all of those things in a software package that you would want to use in real time. So there's going to be a balance between not restricting what you can do and still having chance discovery in the software, but at the same time making it really usable. It's time for questions.
Thank you.
Gina?
Can you say more about the BitBending box or whatever it was called that you are modeling? Like what is that?
Yeah, so let's
Like
try to make sure
really-
we don't hit every single audio example as we go back through.
Yeah.
That'd be something. So in the pictures we showed at the beginning of a couple of pieces I did, we showed two of these Radio Shack project enclosures. And they're actually not that exciting what's inside of them. One of them has a NAND gate. There's long slides. One of them has a NAND gate, so it literally has two banana jacks to allow that to be powered off another board, and then a banana jack for each pin out and pin in on the NAND gate. Where is it? I wonder if it's a clear enough picture to show. So in each row across, we have the two inputs to one NAND gate and one output. And these switches just cascade the output back to the next input if you want to save a banana jack or banana plug. So this is just a NAND gate, and so I think here you can see we're NANDing this signal and feeding the output to here. The other example, which is what we focus on in our modeling, is the counter. So this is two 4-bit counters. We've got the input to each counter and successively more significant bits out. And again, the switch kind of cascades the last bit of the first counter to the input of the next counter to give you an 8-bit counter. So this is taking this signal here, feeding it to the counter, and taking the output and short-circuiting it back to this jack.
Did you make that box?
Yeah, all these pictures at the beginning I made.
Oh, wow, okay.
But what's inside the box is literally one chip on a little perf board thing soldered to the banana jacks. There's nothing else in there. So yeah, actually the boxes are exactly analogous to the chips that we were doing in our model.
You need, I think, if you had the diagram of that in the talk, I don't know. Or,
Yeah, we could show like them side by side perhaps.
oh, yeah, exactly.
Thanks. Roman?
Yeah. So, well, framework. So how is the whole thing implemented? Is it Java, C++, and then how do you actually use it? Do you have some kind of compiler that generates the sound? Do you have, or is it just a library that you use in a like larger framework? Or
So the library is built in C++, and you can make the whole circuit and take the circuit just within the C++ framework. What we have used is a VST plugin. So we've actually implemented the FM synthesis in a VST plugin and used that to get all our examples. But it's basically the library that you can plug into like your own app with your own interface, and that would work.
okay.
Yeah. Julie?
How would you handle analog components? If you're saying you wanted to go to hybrid analog digital, how do you bend the analog stuff? Everything seems to be kind of digitally modified digital.
So it seems that the first step for that is letting the chip in outs handle actual voltages rather than abstract logic highs and logic lows. So there's all sorts of ways that inputs will handle an actual real world voltage, Schmidt triggers and such. So once we have a more nuanced way of handling that, then we can start to combine it into existing models. That's the idea, at least for the first step.
Has anybody ever been like, a real analog synthesizer, just all analog, VCOs and oscillators and, filters and?
People definitely modify them. Circuit bending, like, the borders are kind of fuzzy, but people kind of tend to situate themselves a little bit separate from like the modding community and the modular synth community, because those are more based on kind of tried and true engineering practice. But people do bend purely analog circuits. There's a lot of stuff done with feedback. Feedback is like a really important aesthetic property in circuit bending, these like shrieking, howling things. That's actually a really common feature of many circuit bend instruments, and that's one of the main things we're missing, is we can't implement any feedback. So, people do bend a lot of bends that people do operate only on like an op amp, for instance, that's purely analog, and people modify the feedback paths to get these shrieking things. More questions?
The metaphor from circuit bending to bit bending, where do you think it is really strong, and where do you think it sort of falls short at this point?
Mm-hmm. I think where it falls short is to actually implement a computer model of any sort of circuit bending, be it bit bending or making circuit bend paths on like a SPICE type circuit simulation or a hybrid pi model or something. The problem with the model is you have to build all your assumptions into it. What people find really resonant and exciting about circuit bending, if they don't have an engineering background, is that you can just literally break the back off the thing and go in with like a licked finger or a pair of alligator clips on a diode and figure it out. You don't have to know anything, and you don't have to know why the things are happening. To make these models satisfying and accurate, you actually have to make decisions about what is worth modeling and what isn't. So, for instance, the secret sauce in these things part of it may be that when you make these short circuits, the digital chips stop doing exactly what they've been designed to do. They're driven into saturation, things are going backwards, they're getting signals they don't expect, and the non-ideal behavior is happening. So we would actually have to have a much more nuanced model to take those sorts of behavior into account. Our model makes the assumption that most of the secret sauce in bit bending, the particular type of modification of circuit bending, comes from ideal behavior, and just the fact that serial information as a way of representing different types of signals and different encodings can be mangled up, and that like exposition and like foregrounding of the seams and like the errors in encoding the data is what's important. But that assumption is certainly not completely true. There's definitely other things at play, and because of these assumptions, the model can't foreground those things or get at the exciting things about them. I think what's good about it is, so again, we've modeled actually a thing that doesn't exist as our first example. As far as I know, there aren't FM synthesizers that use two cascaded numerically controlled oscillators. We've actually found references to synthesizers that use numerically controlled oscillators, but not good ones. Like, people just say, yeah, synthesis is sometimes done with numerically controlled oscillators, but usually it seems like function generators use them. So as opposed to the normal kind of modeling ethos where you want to take a real world device you really like, Space Echo or something, and model it down to the finest detail and get everything, we're actually trying to get at just what's exciting about using it and some of the properties of the sound without modeling a specific thing down to the tiniest detail. And actually I think that's what's pretty successful about it. Our kind of demo reel of all the sounds our thing can make shares a lot of the sonic properties and like timbre and time domain, aleatoric sequence generation behavior that the real things have, even though you can't draw a one-to-one comparison and say, here's our real-world device, here's a model of that exact thing, and they have one-to-one correspondence in their behavior and sound. But I think what's the most successful is getting at this feeling and this idea of chance discovery. Okay, if there aren't any more questions, I guess we can call it a wrap.
Thank you.